Hello and welcome to chapter 3. This is all about the atomic structure and the periodic table. First part of chapter 3 is dealing with internal structure of the atom and subatomic particles. Up until the late 19th century, scientists considered the atom to be solid, indivisible spheres without any internal structure at all. Today, this model of the atom is known to be incorrect. There's lots of evidence from various sources to indicate that atoms themselves have substructures, and we're going to examine those substructures. So a very small particle that is the building block of all matter is the atom. Now it's known that there are more than 200 kinds of subatomic particles that have been discovered. We're going to be responsible for only 3 different types of subatomic particles. Those being the electrons, which was discovered by J.J. Thomson, which are found outside the nucleus and possess a negative charge, and they have the lightest mass of all the subatomic particles that we're going to look at. We have the protons, which are found in the nucleus. They are found to have a positive charge. They're equal and opposite the charge of an electron. And the last piece of the puzzle was the neutron, discovered by James Chadwick. This is also found in the nucleus. There's no charge, but it does have an equal mass to that of the proton. Here is just a nice chart showing you the relative charges to one another, relative masses to one another, and the actual masses of the different subatomic particles. So we come to our first learning check. Again, I always encourage you to pause the video and try to answer the questions themselves. But let's see if we could figure out which subatomic particle is given by the description. So it possesses a negative charge, and most of the time we use an E with a little negative sign next to it. Has no charge. Sometimes we use a lowercase n with this naught sign right here. Has a mass slightly less than that of a neutron, and that is going to be a proton. Sometimes we will put a little plus there. And the last one, D, has a charge equal to but opposite sign of that of the electron, and that again is our proton. Here is our second problem for dealing with subatomic particles, and we're going to indicate whether the following statements about the nucleus or of the atom is true or false. The nucleus of the atom is neutral for A, and that is a false statement. Nucleus should be positive. Nucleus of an atom contains only neutrons. That's false as well. It should have protons and neutrons. C, the number of nucleons represented in the nucleus is equal to the number of electrons outside the nucleus. That's false. In a neutral atom, protons and electrons might be equal to each other. And our last one, the nucleus accounts for almost all the mass. That is true. Electrons weigh almost nothing compared to the protons and the neutrons. The nucleus is composed of protons and neutrons. It's relatively small in comparison to the overall size of the atom. However, it's extremely dense and accounts for almost all of the mass. The nucleus is positively charged due to the fact that it has protons and neutrons. So a little circle with a positive, that's our proton. A little circle with nothing in it, that's our neutron. And then we have our electrons whizzing around here in some weird orbital shape. And I'll put a little minus sign by that electron. So for the most part, when we look at atoms, they're going to be electrically neutral. That means we have just as many protons in the nucleus as we do have electrons roaming around the nucleus. For section number 2 of chapter 3, we're going to be looking at the atomic number, mass number, and trying to determine how many protons, neutrons, electrons something has. So the atomic number, the Z atomic number, is sometimes known as just the number of protons in the nucleus. Well, it's always known as the number of protons. The mass number is the sum of the protons and the number of neutrons in the nucleus. And we have symbols that we help that help us figure out how many protons, neutrons, electrons something has. So this could be any symbol off our periodic table. This is the mass number up here. This, remember, is our protons plus our neutrons. And this down here is just the number of protons. So if I were to subtract these two numbers, I eliminate all the protons, and I have a very easy way of determining how many neutrons something has. If there's a charge, it will be written up here. Right now, everything is electrically neutral. We don't have to worry about charges just yet. An element is a pure substance. We covered that in chapter 2, in which all the atoms present have the same number of protons or the same atomic number. This is like a fingerprint to you and I. Same thing with atoms. You figure out how many protons it is, you can figure out what the element is. All atoms with the same atomic number are going to have the same chemical properties and are going to be considered the same element. Again, I encourage you to pause the video and try to answer these questions for yourselves, and then check and see if you got them right. But we're looking for how many protons, neutrons, electrons something is present, and everything we'll consider right now to be electrically neutral. So I like to write these with our mass number on top, our atomic number on the bottom. You could figure out what element this is on our periodic table, but we really don't have to. So to figure out our number of protons, that's just our bottom number. So our protons is equal to 7. We would get our neutrons by subtracting these two, and our neutrons would be, in this case, 8. And since we're electrically neutral, our protons and electrons should be equal to each other, so there's 7. Doing the same thing here, 40 and 20. Remember, protons is equal to the bottom number, so that's our protons. Subtract the 2, you get the number of neutrons. So our neutrons is equal to 20. Just like our protons was, and our electrons and protons are equal to each other, so 20. Here they're giving it to you in a slightly different way. This is the number of protons, and it's the number of electrons. And if we were to subtract 11 out of here, we would end up with our number of neutrons, which in this case is 12. Same thing is true here. Our protons and our electrons are equal to 35. And again, if you were to subtract these two numbers, you would end up with 44. Section 3-3 deals with isotopes and atomic masses. So to define what an isotope is, it's going to be atoms of the same element that have the same number of protons or the same atomic number, which means they have the same number of electrons, but they have different number of neutrons. So our mass number is going to be different. They show almost identical chemical properties because everything in chemistry and their chemical properties is going to be based off electron properties and their configurations. Physical properties are often slightly different because they have different masses, and in nature most elements contain a mixture of isotopes. Here are some notations for isotopes. Okay, notice the bottom number, 11, is the same for sodium. Again, that's the fingerprint that's going to determine its identity. But our top number here can vary. The number of neutrons in the nucleus can vary from one atom to another. So again, this is showing us we have 11 protons. Our mass numbers are different. Number of neutrons are different. And hydrogen has 3 different isotopes that are out there, and a lot of times they're just denoted by the number up on top: hydrogen 1, hydrogen 2, and hydrogen 3. Here's another learning check for us, trying to figure out how many protons, neutrons, electrons there are. So again, I encourage you to pause the video and see if you can figure it out. But protons, neutrons, electrons, right now everything is electrically neutral, so if there's 50 protons, there must be 50 electrons. If we were to subtract these two numbers, we would end up with 68 neutrons, protons, neutrons, electrons. Again here, these are equal, 78 and 78. And if I were to subtract these two numbers, I would end up with 117 neutrons. Doing the same thing here, 31 protons, 31 electrons. Again, just subtract these two numbers and you end up with 41 neutrons. And one last one just for practice, 12 protons, 12 electrons. Subtract these numbers and you end up with 14 neutrons. One more learning check for us. We're going to be given an isotope X that contains 23 protons and 28 neutrons. First one wants to know the mass number. So all we got to do is add up our protons and neutrons and we get our mass number. In this case, 23 plus 28 is going to give us our answer of 51. Then we just have to find 23 on our periodic table, and it happens to be something in the transition elements known as vanadium, or capital V. The next part of this chapter deals with how we figure out that decimal number that's on our periodic table, and that's going to be concerned with more of an average of all the isotopes that are out there. So there's really going to be 3 steps that you're going to follow. Let me write them here for you. Step 1 is to convert this percent into a decimal. So you're going to change your percents into a decimal. And that's pretty easy to do. All you got to do is take your decimal and move it over 2 times to the left or divide by 100. Step number 2 is take that decimal number and multiply by the mass that's given. Step number 3 is to add all of your results. The 3 steps that I described on the last slide are done here, where we take this percentage and turn it into a decimal and then multiply it by its mass. That's what's happening here. Take this percent, express it as a decimal, so move your decimal over 2 times, then multiply it by its mass, add up all of your results, and that's how you get the decimal number that's on our periodic table. Here's another learning exercise. Again, take this percent, we'll move our decimal over 2 times, and you end up with 0.6260 times our mass of 186.956. That's going to be equal to 117.034456. Going to do the same exact thing with our other one and our mass. So this is going to be 0.3740 times our mass of 184.953. And that's going to get you 69.172422. I ran out of room there. Now you just have to add these 2 steps up together, and you're going to end up with 186.206878. Looking at these digits right here, we have 6 significant figures. So we kind of keep it the same. Here's our 6th significant figure. This one is big enough to make us round up to the top, or round up to a 7. So 186.207 will be our answer. And there is the average atomic mass that it wanted you to find, and then you look up this on our periodic table and you would find that that one belongs to the element Re. This is going to be more of the same. Again, I encourage you to pause the video and try these for yourselves, but move this decimal over 2 times, so it's 0.0742 times our mass of 6.01. When you do that, you'll end up with 0.446. Do the same thing with the next one. It's going to be 0.9258 times our mass of 7.02. That's going to give you an answer of about 6.50. Add those 2 results and you'll get the answer that's expressed right there. When you do this, you'll get 6.946, and this is big enough to make us round the 4 up to a 5. Going to do the same exact process for B, and I'll just give you the answer. Try it for yourself. During the mid-19th century, scientists began to look for order in an increasing amount of chemical information that had become available. They knew that certain elements had properties that were very similar to those of other elements, and they sought reasons for the similarities in the hope that these similarities would suggest a method for arranging or classifying the elements. In 1869, these efforts were accumulated by the discovery of what now is called the periodic table of elements and the periodic law. So the periodic law states that when elements are arranged in order of increasing atomic number, or the number of protons, elements with similar chemical properties occur at regular occurring intervals. Thus, Dmitry Mendeleev constructed our first periodic table of elements that is still revered today as a major accomplishment for this. Dmitry was one of 13 children, the youngest of 13 children in a Russian family, and had quite a knack for organizing things. His periodic table left blanks for elements that were not yet discovered, and when they were discovered, his predictions of their physical and chemical properties were spot on. In addition to being able to figure out the number of protons, neutrons, and electrons from a periodic table, there are other things that you should know about it as well, such as that periods are the horizontal rows. There are 7 of them on our periodic tables, and groups go up and down, and they have very similar physical and chemical properties. There are 18 of them on our periodic table, at least the condensed version there is. Here's a nice picture of the periodic table, where we're going to label a few things, and you're going to need to recognize a few things. First thing we'll talk about are these A groups. These are sometimes known as the main group or representative elements. And then we have our B groups in here. Sometimes these are known as our transition elements. So the A groups were the representative. Sorry about the chicken scratches. Group 1A is sometimes known as the alkali metals. Group 2A are known as the alkaline earth metals. This group over here, 17, are sometimes known as the halogens, and 8A are known as the noble gases. There's a division line right here, hopefully you can see. That's going to separate our metals from our non-metals. These over here are our metals, and up above here are where you'd find liquids and gases, so we call this section the non-metals. If it's touching the staircase, directly above or below, not kitty corner, sometimes those are known as the semi-metals or metalloids. Groups, again, go up or down, groups, families. And periods go left to right. This will eventually be known as our S block. This will be our D block in here. This will be our P block from here to here. D goes from here to here. S is just 2 families wide, and our F block will be down here. Here's just a table telling you about some of those families or groups that I mentioned previously. It does do a nice job and give you the most likely charges of some of those as well. And we'll give some more charges later on. This exercise is designed to get us somewhat familiar with finding elements on our periodic table. So we're going to give the period and group number. So beryllium is found right here. It's in period 2, group 2A. Phosphorus is found over here. It's found in period 3, group 5A. Potassium is located right here. It's in period 4, group 1A. And iodine is found right here. It's found in period 5, group 7A. And they should be given in Roman numerals, so this will be Again, I encourage you to pause the video and see if you can answer some of these questions about the periodic table. So for part A, we're looking for the atomic number of carbon. Carbon is right here. Our atomic number is 6. For part B, the atomic mass of the element silicon, it's right underneath carbon. Our atomic mass is 28.09. The atomic number of an element whose atomic mass is 88.91, we would be looking for number 39. And our last question, the atomic mass of an element located in period 2, group 2A. So period 2, group 2A, playing battleship, we would have beryllium. And our atomic mass is 9.01. For the next one, we're just going to see if we can figure out of these elements that are listed, which ones have similar chemical properties. So we'd be looking really for the same group. And for A, it would be K and Rb. They're both found in group 1A. For B, we would be looking for P and arsenic. They would be found in group 5A. For C, we would be looking for F and I. They would be a halogen, so they would be located in group 7A. And for D, we would be looking for sodium and cesium. They are located in group 1A. A little bit more practice with our periodic table. We'd be looking for a specific color to answer the question. So we're looking for the highlighted element that's a halogen. That's found in group 7A, so that's our blue. Which of the highlighted element is the alkaline earth metal? I always remember that that has 2 parts to his name, so that's in group 2A, so that is the yellow. Which element highlighted is in group 2A? That's yellow again. And which one is in period 3? Remember, periods go this way, so period 3 would be our green. We noted in our previous section that group 1A and 2A were known as the alkaline and alkaline earth metals. So we're going to define what metals are. These are elements that have a characteristic property, that of luster, thermal conductivity, electrical conductivity, and malleable. Here's just some pictures showing you some of the different metals, and you'll probably encounter some of those in lab. When we were drawing our periodic table or highlighting it, we noted that staircase, and the elements directly to the right of that were nonmetals. These can be characterized by the absence of luster, thermal conductivity, electrical conductivity, and malleability. Here's some pictures of some nonmetals. Here's a nice chart noting some of the different physical properties of metals versus nonmetals. I encourage you to pause this video and just read through those real quick. Here is our staircase that divides the metals and nonmetals. And remember, if it's directly above or below, with one exception being aluminum. Those would be metalloids. So this is a metalloid here, here. These elements right here are considered metalloids, where their properties are somewhat in between metals and nonmetals. Just a good idea to put this little staircase in here, so hopefully I traced that right and did it kind of quick, but that's going to help us determine what's a metal and a non-metal. So when we're looking at the red, that's a metal. Element highlighted in green, that's going to be a non-metal. Element that's highlighted in yellow would be a poor conductor of electricity, and the element highlighted in blue would be a good conductor of heat, because it's a metal. The next section of this chapter deals with the electron arrangements. And electrons move about the atom's nucleus and are restricted to certain regions around that nucleus. Such restrictions are determined by the amount of energy that an electron possesses, and furthermore, they're limited to certain values and specific behaviors within each energy level. So an electron shell is a region of space around the nucleus that contains electrons that have approximately the same energy and spend most of their time in the same basic distance from the nucleus. Electrons that occupy the first energy shell are closer to the nucleus and have lower energy than those in the second, third, or fourth shell. Within each shell, electrons can be further divided into electron subshells, and these are much more restricted areas of space within each electron shell that contains electrons that have the same amount of energy. There are 4 different types of subshells for our class. There's going to be the S, P, D, and F, and we kind of labeled those on our periodic table a while back, if you remember. The maximum number of electrons within each shell is given to the right in the chart. So the S has a maximum number of electrons of 2, P 6, D 10, and F has a maximum number of electrons of 14. Electron subshells within them have a certain definite number of locations that we call orbitals. A region of space within each electron subshell where an electron with a specific amount of energy is most likely to be found. And when we draw these, we'll find that there are a maximum of 2 electrons per orbital. Soon enough, we'll see the shape of some of those orbitals, but rather than trying to draw those, because I'm not a very good artist, we're going to draw them as boxes. So our S subshell has 1 orbital designated by 1 box. Our P subshell has 3 orbitals. They're going to look like dumbbells, and they're going to be 3 boxes, or your book might use circles. D is going to have 5 boxes, or 5 circles. And F's will have 7 boxes or 7 circles. I'm not sure which one your book uses. Here's just a drawing showing some of the different shapes of those orbitals. And again, drawing these would be almost impossible because there are 3 different orbitals. There would be the ones located along the X, the Y, and then the Z where it's coming out of the page at you. There would be 5 of these shapes and 7 of those. Trying to stack those on top of each other would be a nightmare for an artist like me. Here is a much better picture showing those p orbitals on the 3 different axes. Experimental studies indicate that an electron moves about within an orbital, and it spins on its axes in an either clockwise or counterclockwise direction. So when we draw these, when we draw those boxes, we're going to draw the clockwise and counterclockwise going in certain directions, and we'll do one like this. It's important to recognize that we can never have 2 up arrows or 2 electrons spinning clockwise or 2 spinning counterclockwise. They have to be going in opposite fashions if they are in the same orbital. And when we fill in this could be something like a P5. We would go up all the way across. We don't pair up until we have to, and then we're forced to pair up on the way down. So that's how we would fill in something like 2p5. Again, I encourage you to pause the video and try to figure out if you can figure out if these are true or false statements. So in A, an orbital has a definite size and shape which are related to the energy of the electrons. That is a true statement. Next, all the orbitals in the subshell have the same energy. That is true. Orbitals in the subshell have the same amount of energy, although they might differ in orientation. Next statement, all subshells accommodate the same number of electrons. That's false. The S, P, D, and F all have different number of electrons that can fit in their orbitals. And the last one, 2p subshell and a 3p subshell contain the same number of orbitals. That is true. Now we're going to put everything together, and we're going to have some rules for assigning electrons to various shells, subshells, and orbitals. First one is that electrons fill the lowest energy level first. Second rule is that we have to fill in one all the way across before we come back in and fill down. So if you're going to fill everything with one single electron, they all have to have the same spin. Usually they're going up, up, up. Third rule is that we can have no more than 2 electrons per orbital, and if they do have 2 electrons, they have to be spinning in opposite directions, so the arrows need to be pointing in different directions. Here's a nice diagram showing you the order of fill for our electron configurations. We always start at this arrow right here. There should be a 2 on all of these S's. There should be a 6 on all of the P's. Should be a 10 on all of the D's. And there should be a 14 on all the F's. So we fill them in this way here. All we have to do is really add up our exponents until we get to the number of electrons that we wanted. We can make our exponents smaller, we can never make them bigger. And it's important that you follow the path of the arrows and never get off the path of the arrows. Don't read this like a book. Follow the path of the arrows until you get to the number of electrons that you want, and you do that by adding up your exponents. So electron configurations give the precise location of electrons in their subshells for a particular element. So oxygen, when you find it on your periodic table, you'll see that it has 8 electrons. The symbol would look like, give me a second here. Oops. Oxygen would be 16 and 8, meaning that it has 8 electrons. We need to follow that arrow diagram until we reach 8 electrons. I'm only going to draw a few here. But we start right here. We go 1s2, that's the first part. We're done with that arrow. We jump to the second arrow, follow it until it's done. That's how we end up with 2s. Jump to the third arrow, and we only need to use the first little bit that we get to, the 2p6, but I don't need 6 of those electrons. I only need 4 of them, because if I add up my exponents, it should be equal to 8. So 2 plus 2 plus 4 is 8, and that's the number of electrons that I wanted. If I needed more, then I could have 2p5 or 2p6, or I could continue on my arrow diagram. Here we're going to write the complete electron configuration for the following atoms. So here we need to get to 6 electrons. So I'd follow the arrow diagram. 1s2, 2s2, and then you'd end up at 2p6, but I don't need all 6 of those. I only need 2 of those. So my complete electron configuration would look like this. Sodium, I end up with 11 electrons, so I got to go past where I did for the carbon. And following those until you get to 11, you would end up with this electron configuration right here. Sulfur, I got to get to 16. So I start with the first arrow. There's 2. Here's 4. Here's 10, 12. And now it needs some from this one right here. But I don't need all of them. I just need a portion of it. And I'd end up with 3p4. Argon would be up to 18. Okay, and you just end up with 2 more than you had for the sulfur, and you'd end up with this electron configuration right here. For this problem set, we're trying to identify which element has this electron configuration, so you just have to add up your exponents. Here you add up with, you get 8, and we know that's oxygen. Here, this looks like it's about 10, so we know that one is probably neon, I'm guessing. Yeah, neon. Adding up these, 2, 4, 10, 12, 13. For 13, we would end up with aluminum. And on this one, once you add up all of those electrons, there's 20 there, and 20 is calcium on our periodic table. Now we're going to put these electron configurations together with orbital box diagrams, and this is just showing us the electrons in the boxes that are represented here. So S has 1 box, P has 3 boxes. Notice the number of electrons present is 2 here. Those 2 electrons are going to go in here, and we'll have 1 up, 1 down. Same thing is going to happen here. But this one only has 4. Remember, they fill in up, 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 and then they come back in and fill down. So here's our 2 electrons. Here's the next 2 electrons. And then this one up, 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 and then they come back in and fill down. Notice that there are 2 vacant spots. And this is probably why oxygen has a 2- charge. It's going to pick those up from someplace else. Here we're going to draw some of the orbital box diagrams that go along with our electron configurations. So probably the most important thing here is to denote the last one. Okay, there's only 2 electrons in the p orbital, and they're both in the up direction. And this is what I was talking about. Some books use circles, some use squares. In the next one, everything is going to be completely filled. And notice the up and down arrows in each one. Next one, in the last one, our p orbital is only got 3 electrons in it. So everything before will be completely filled, 1 up, 1 down. But our last one only has 3 up arrows in it. And in D, we end up with a d orbital. Remember, those have 5 boxes, or in this case 5 circles. And we have to go up all the way across and down in the last 2 in that d orbital. So we end up with something that looks like this right here. Here's just another exercise trying to get us to write electron configurations. So you're supposed to do one for sulfur and for barium. There's what your sulfur looks like. Barium has a few more electrons in it, so it would take a while to add these up. But when you're done, you end up with something that looks like this. This is going to show us why electrons are largely responsible for chemical and physical properties. It's because the outermost electron shells have the same number of valence electrons in them, and that's going to be true for elements in the same group. So if we take a look at group 1A, these are very, very reactive, especially if you put them in water. Notice highlighted in red, they all have S1 at the end of their electron configurations. That means they have 1 valence electron in their S shell. The only thing that's varying is the number there, and that corresponds to the period on our periodic table. Here's a picture of the S, D, P, and F block. Notice anything in the alkaline metals would end in S1, alkaline earth metals end in S2, halogens end in P5, and our noble gases end mostly in P6 with the exception of helium. Here is another learning check for us. We're going to try to indicate whether elements present in a pair have similar chemical properties. And basically they would end in the exact same way if they had similar chemical properties. So these do not end in exactly the same way, so this would be a no. P6 and P6, you would put yes here because they end in P6s. P3 and D3, they both end in 3, but you need the same letter as well, so this would be a no. And 3P4 and 4P4, and you would put yes here because they both end in P4. Here's another question for us. Again, pause the video, see if you can get what the highlighted question mark or highlighted element is. So is the element highlighted in red in the S or P? Well, that's in the S area of our periodic table. Element highlighted in green, that's in the D area of our periodic table. Highlighted in yellow, that's going to be a P4. And highlighted in blue, that would be an S2. Distinguishing electrons. The last electron added to our electron configuration is probably the most important. It's going to have the highest energy, and it's going to cause our electron configuration to differ from the element immediately preceding it on the periodic table by one element, giving it different chemical properties. Elements can be classified in several ways. The two most common classification schemes are listed here. The first one is based on their physical properties, in which you could describe them as metals or nonmetals. And the second system is based on their electron configurations, in which elements are classified as noble gases, representative, or transition or intertransition elements. Here's just a picture showing us the second classification scheme. Congratulations on making it to the end of this slideshow. We're going to end with one last learning note, and we're going to try to classify the elements as one of these different types. So phosphorus is found right here. That's going to be a representative element. Argon is found over here. That's going to be a noble gas. Au, give me my gold, is right here. That's a transition element. And uranium is way down here. That's going to be an intertransition element. Thanks for bearing with me. See you next time.